maximum subarray. What if I told you there's one simple algorithm that unlocks dozens of tough interview problems? Maximum subarray is a Pattern Mastery 100 legend and shows up in interviews at Microsoft, Amazon, and Google. More than half of candidates overthink it, but once you know the trick, you'll solve it in seconds, no matter how big the array. Let's learn the pattern that makes dynamic programming click. Let's break it down. Given an array of integers, both positive and negative, we're looking for the maximum sum of any contiguous subarray. In other words, what's the biggest slice of the array we can add up? If the whole array is negative, pick the least bad number. Now let's assess. A brute force approach checks every possible subarray, n squared time. That won't work for big inputs. But what if, as we scan left to right, we keep a running total? If that total ever goes negative, we start over, since a negative sum can only hurt us. This is the magic of K-Dane's algorithm. At each position, decide if you're better off starting fresh or extending the current sum. Here's the structure. Initialize two variables, current_sum, the best sum ending here, and max_sum, the best overall. Start both at the first number. For each new element, update current_sum as the higher of the number itself, or the number plus current_sum. Update max_sum if current_sum is higher. Return max_sum at the end.
Let us try to implement it using solution 1. We begin by declaring the solution class. This is simply the container for the method. We then define the max_sub_array method. It takes an array of integers and returns the largest possible sum of any contiguous subarray. Next, we store the length of the array in a variable called n. This keeps our code tidy and readable. Here we create a DP array of size n. DP at index I will represent the maximum subarray sum ending exactly at index I. We initialize the first element. The best sum ending at index 0 is simply the first number itself. We also create a variable called max to keep track of the best overall subarray sum we have seen so far. It starts off as the first element. From there, we begin a loop starting at index 1 and moving to the end of the array. Since we visit each element once, this loop runs in O of n time. This is the key dynamic programming step. For each index I, we set dp at I to the maximum of two choices. First, nums at I by itself. Second, dp at I-1 plus nums at I, which means extending the previous subarray. We take whichever option gives the larger sum. Next, we compare the new dp value at I with our running global maximum. If dp at I is larger, we update max. That means we have found a new best subarray. That ends the loop. At this point, we have computed the best subarray ending at every index. And finally, we return max, which holds the largest sum of any contiguous subarray in the entire list. And that is how this algorithm works. It initializes a dynamic programming array to track the best sum ending at each position. Then it moves forward, either growing the current subarray or starting fresh, depending on which choice gives a larger sum. All the while, it remembers the best total seen. Efficient. Simple. Clear. Check. This test validates the maximum subarray solution, which identifies the largest possible sum of any continuous subarray. Nums equals -2, 1, -3, 4, -1, 2, 1, -5, 4. The idea is to track a running sum and reset it whenever it becomes negative, while also keeping track of the highest sum seen so far. After some early fluctuations with negatives and small positives, the subarray starting at the number 4 becomes important. The sequence is 4, -1, 2, 1. These four numbers form a continuous block. Their total is 4 plus -1 plus 2 plus 1, which equals 6. This value of 6 becomes the best overall sum. The numbers that come after this block do not create a higher total, so the maximum subarray is the sequence 4, -1, 2, 1. Its total sum is 6. The output is 6, matching the expected 6. The algorithm correctly identifies the continuous segment with the highest possible sum. Now let us try another implement approach using solution 2. We begin by defining the solution class. This is the container for our optimized method. Then we declare the max_sub_array method. It receives an array of integers and must return the largest possible sum of any contiguous subarray. Next, we initialize two important variables. Cur represents the current running subarray sum. Best keeps track of the largest subarray sum seen so far. Both start at the first value in the array, since every subarray must include at least one number. After that, we begin looping through the rest of the array starting at index 1. Since we examine each number once, this loop runs in O of n time. This line is the heart of Kadeni's algorithm. We set cur to the maximum of two choices. 1. Start a new subarray at the current number. 2. Extend the existing subarray by adding the current number to cur. Whichever choice produces the larger value becomes the new cur. Then we compare cur to our global best. If today's running sum is the highest we have seen so far, we update best. That wraps up the loop. By now, we have evaluated every possible subarray ending position in one efficient sweep. And finally, we return best, which is the maximum subarray sum found across the entire array. And that is how this algorithm works. It begins with a running sum and a best sum. It updates them as it moves through the array, choosing at each step whether to continue the current subarray or start fresh. In the end, it finds the maximum sum in linear time. Efficient. Simple. Clear. Check. This is the simplest possible case for the maximum subarray problem. Input. Nums equals 1. With a single element in the array, that one value is the only subarray that exists. Its sum is simply 1. No comparisons, resets, or extensions are needed. So the maximum subarray sum is 1. The output is 1, matching the expected one. The solution correctly handles the single element edge case.
Let's have a quick recap. Breakdown recap. This problem asks for the maximum possible sum of a contiguous subarray, essentially, the best slice of numbers you can take from the array. It's simple in wording but powerful in concept, because it's all about identifying where a subarray should start and stop to maximize value, even when negatives appear. Assess recap. We began by comparing strategies. The brute force approach tries every possible subarray, but that's far too slow. The insight comes from recognizing a pattern. If your running total ever drops below 0, it can only hurt future sums. That's where Kadeni's algorithm shines. It teaches you to reset and rebuild intelligently as you move forward. Structure recap. The structure revolves around two trackers, one for the current running sum and one for the overall maximum. As we iterate through the numbers, we decide whether to extend the current streak or start fresh at the current element. At every step, we update the global maximum if the new running total is higher. Implement recap. Conceptually, the implementation mirrors human intuition. We process the list one element at a time, adjusting our ongoing total as we go. Each decision point asks, does this help my sum, or should I restart? That simple comparison powers the entire solution with just a few lines of logic. Check recap. When we tested the sample array, the logic worked perfectly. The algorithm built up a sequence of positives, ignored harmful negatives, and landed on a maximum sum of 7. Even if all numbers were negative, it would still pick the least damaging one, consistent and efficient every time. The key takeaway is that optimization often comes from recognizing when to let go. Kadeni's algorithm isn't about complex math, it's about making smart, local decisions that add up to global success. Once you internalize this pattern, dynamic programming and problem-solving under pressure start to feel natural.